the learning intention for this lesson is to be able to derive and use the constant acceleration formula. And the most important part of that is constant acceleration. So in chapter 11, we're going to be looking at when the acceleration varies. But for now, we're sticking with a constant acceleration. So we might have an object that is moving from one place to another. It's speeding up, but the rate of change of velocity is always constant. So the acceleration is always maintaining as a constant value. Now, to be able to do these formulas, we need to have some standard set of letters. So the first one is an S to represent displacement. And we've actually already seen this before when we looked at displacement time graphs, because we had displacement on the y-axis and we used an S to represent that. On the x-axis, we had time and we used a T to represent time. And that's what we're still going to do. So we've got a T here that represents the time. Now, if I've got, so here's my object. It's here in one position, the initial position, and then the final position. And we've just said that the displacement that it's moved is used to represent, uses the letter S to represent it. And that it takes a time t. Now, the velocity it is moving with at the start, the initial velocity, we are going to use a U to represent. So a U represents my initial velocity. And at the end, the final velocity is represented by a V. So a V represents the final velocity. And then the acceleration that it goes through, the constant acceleration, because we're only looking at constant acceleration at the moment, is represented by an A. So that's our final letter, A. And actually these first letters, so we've got S, U, V, A and T, they make the word SUVAT. And that's how we often refer to the formulas we're going to derive now. We call them the SUVAT formulas or the SUVAT equations because those are the letters that we use. Now, I want to flash our minds back to earlier on this chapter when we looked at velocity time graph. So here's a velocity time graph. We've got velocity on the y-axis and time is on this x-axis here. And this velocity time graph has a straight line that's going up. Now, we said that a straight line on the velocity time graph that is increasing, so the gradient is positive, shows an acceleration. And we said that the gradient on the velocity time graph is the acceleration. So I can say here, I've got my gradient. And if I want to work out the gradient of this line, well, I know that the gradient is the change in y. Well, here, the change in y is represented by V minus U, the final velocity minus the initial velocity, V minus U. And then over the change in x. Well, the change in x is just the time, so it's t minus 0, but we can just write t. So the gradient is v take away u all over t, which is my time. Now we've just said that the acceleration is the gradient, so I can say acceleration is equal to v minus u all divided by t. If I rearrange that slightly, I can multiply by t, and I could also take the u to the other side. I will get the formula v equals u plus at. It might be worth just checking on a spare piece of paper that you can rearrange that to get to here, v equals u plus at. And that is my first SUVAT equation. So I'm going to write it here where I've got equation 1, v equals u plus at. Now that is something you just are going to have to remember. But if you don't remember it, you can always remember how you derive it from the graph, and that is something you need to know as well. So that is our first formula. V, the final velocity, is equal to u, the initial velocity, plus the acceleration multiplied by the time. V is u plus at. Right, we also said, as well as the gradient showing the acceleration on a velocity time graph, we said that the area under the graph shows the displacement. So I've got the area here, shaded in on my one, is the displacement. Now if I want to work out my area, what I've got actually here is a trapezium. If you think about it, you probably normally think about trapeziums on their side. This one's a stood-up trapezium. And I can work out the area of my trapezium. Well, the area, this side here is length u. This whole side here is length v. So the area is u plus v over 2, all multiplied by t. That's how I work out the area. And I can write that as S equals u plus v over 2 multiplied by t, because we know S, the displacement, is the area. So displacement equals u plus v over 2 multiplied by t. And I can leave it like that, or I could rearrange it if I wanted to. I'm going to leave it like that. That is my second SUVAT equation. I'm going to write that again down here next to this. So S equals u plus v over 2 all multiplied by t. And if you want to somehow highlight that box we've got down there, they are our TBAT equations that we have found so far. And I would recommend learning these. You need to know how to derive them, but it's also nice and easy to know them off the top of your head. Right, so let's have a look then at example 4. We've got a cyclist travelling along a straight road. So here's my straight road. I'm not going to try and draw a cyclist, I'm just going to draw them as a dot for now. So we've got the cyclist travels from here and she's going to end up over here. And she's accelerating at a constant rate. So I know we can use the TBAT equations because we've got a constant rate, which means an acceleration, a constant acceleration. It says from a velocity of 4. That must mean that at the start she is moving at 4 meters per second. So I've got that u is going to be 4 meters per second. And that her final velocity over here is 7.5 meters per second. And it took 40 seconds. So what I'm going to do is I'm going to write out what I know so far. Let me just fit that on here. So I'm going to write out what I've got, the information I've been given. So we don't know anything about the displacement yet, and in fact I can kind of see that's what I'm going to be having to work out. But I do know the initial velocity. I know that u is equal to 4 meters per second. I know the final velocity. I know that final velocity is 7.5 meters per second. I don't know the acceleration, although I do know it's constant, and I do know the time. It's going to take her 40 seconds. And part A is asking me to work out S, so work out the distance that she travels in those 40 seconds, working out her displacement. Well, looking at these two formula that we've just derived, I can see clearly I'm going to be using formula number 2. Yeah, that's the one that's got an S in. Formula 1 wouldn't help me if I'm trying to work out the displacement. So I'm going to use S equals u plus v all over 2 multiplied by t. And I'm going to substitute in what we know. So I know that u is 4, so I'll put 4 plus v is 7.5, all divided by 2, and multiplied by 40. That's what I get for t. Now obviously you'll do that on your calculator because we have our calculators for this exam, and that's 230 meters. So the distance she travels in 40 seconds is 230 meters. Part B is asking me to work out the acceleration. So looking up here, I can see that I'm this time going to be using formula number 1 because that's what's got acceleration in it for me. So I've got that v equals u plus at. And what I'm going to do is I'm going to rearrange to get a on its own. Now check that you can definitely rearrange this. It should be nice and simple. I'm going to take the u over and divide by t. So I get v minus u divided by t. So again, I'm going to be substituting in. So for v, I get 7.5. So 7.5 minus u, which is 4. All divided by the time, which is 40. Typing that in. And what we should get is 0.0875 meters per second squared. And don't forget, meters per second squared, there are units of acceleration. So my acceleration in that time is 0.0875. Right, let's move on then to the next example. So example number 5 is on this next page. So we've got a particle moves in a straight line from point A to point B with a constant deceleration this time of 1.5 meters per second squared. The velocity of the particle at A is 8 meters per second and velocity at B is 2 meters per second. Let's then draw a quick diagram to represent that. So I'm going to do it up here, I think. So we've got a point here, A, and it's moving over to a point called B. And this time the deceleration is 1.5. Now I'm going to write that as an acceleration of negative 1.5 because I know that if it's decelerating by 1.5, that is the same as a negative acceleration. It says the velocity at A is 8. So the initial velocity at this point here must be 8 meters per second. And at B, it's 2 meters per second. That is my final velocity. And it says find the time taken to move from the point A all the way to the point B. So let's start off by writing out what we know so far. So SUVAT, that's how I'm going to start most of these questions. And I'm just going to be clear, I should have probably put this above, that I'm currently talking about going from A to B, from the point A to point B. We don't know the displacement yet. I do know the initial velocity, that's 8 meters per second, that's the speed at point A. I know the final velocity is 2 meters per second, that is the speed at point B. And I also know the acceleration is negative 1.5. Oh, I've just messed up there. Negative 1.5 meters per second squared. Sorry about that. You can still read that. That is a negative 1.5. So, firstly, it's asking me to find the time taken. I'm going to use that equation 1 that we looked at before, v equals u plus at. And that's because I've got v, I've got u, I've got a, but I'm trying to find t. So I'm going to rearrange, and I'm going to see that t is equal to v minus u, all divided by a. Check again that you can rearrange that equation nice and easily. So therefore, t is equal to, instead of v, I'm using 2 meters per second. Take away u, so minus what I've got for u, which is 8, and divided by the acceleration, which is negative 1.5. Type that all into your calculator, and you'll get that t is equal to 4 seconds. That is the time taken to move from A to B. This time, part B is asking for the distance. So I'm going to use the other formula, that second formula we looked at, which is S equals u plus v all over 2 times by t. And again, same as before, I'm going to be just subbing in the values that I've got into that equation over there. So instead of u, I'm using 8. I'm going to use 2 for my v, divided by 2, and times by the time. Now I've got the time because we've just worked it out, so the time is equal to 4 seconds. And if you type that all in, you should get it's 20 meters. That is your displacement from A to B. So we got 20 meters as my answer there. So we got 4 seconds for the answer to part A. Now, it goes on to say, after reaching B, the particle continues to move along the straight line with constant deceleration of 1.5 meters per second squared, same as before. The particle is at the point C 6 seconds after passing through point A. Find the velocity at C and the distance from A to C. Right, well, might be a good idea then to do another diagram. So this time I'm only bothered about from A to C. So my initial particle is at the point A and it ends up at the point C. And I know that the time it takes to get from A to C is equal to 6 seconds. I know that the acceleration is still negative 1.5 meters per second squared. And I actually know the initial velocity, because the initial velocity is still going to be 8 meters per second. That's what it started off as, and we're still thinking about when it was at A, that's what it was moving at. So the initial velocity is still 8 meters per second. Let's do then our letters. Let's see what we know. So we've got S, U, V, A, and T. And obviously this is different to before because we're looking at going from A to C. Whereas before we looked at A to B, here we're looking at A to C. I don't know the distance yet. What I do know is the initial velocity is 8 meters per second. I don't know the final velocity. I don't know what it's moving at point C. Do not know the velocity there. I know the acceleration is still negative 1.5 meters per second squared. And I know the time this time. I know that it takes 6 seconds to move. So part C says find the velocity at C. So I'm trying to find what V is equal to. And I'm going to use equation 1. V equals U plus AT. So V is equal to, U is 8, A is negative 1.5, multiplied by the time, which is 6. Substituting all that in, I get that the velocity at C is negative 1 meters per second. Now, we might think that's a bit strange, negative 1, but remember, velocity is a vector. So the negative just tells me that the particle, instead of moving to the right, the positive direction, this time it must be moving to the left because it's moving at negative 1. So it's going 1 meters per second, but this time to the left rather than to the right. And that's perfectly fine. It doesn't matter that we've got a negative there, it's just telling us the direction of the particle. Now if I look at part D, it wants the distance, so it wants me to work out what S is. The displacement from A to C. So I'm going to use equation 2. S is equal to U plus V all over 2 multiplied by t. And I'm going to substitute everything I know in again. So I know u is 8. This time I know v, because we've just worked out, is -1. And remember, you still need to keep that -1 in there. Divided by 2, or multiplied by the time, which is 6. Substitute all that in, and we should get an answer of 21 meters. That is my displacement. So just to be really clear, I'm just going to highlight what I got for my answers there. I got the time, the displacement, the velocity, and the displacement there. Those were my answers. And I think it really helps to be super clear. So if you have an exam question, if you make sure you're writing out the S, U, V, A, and T values, they can see exactly what you can see what you know, and you can see what you're trying to work out. Right, let's have a look then finally at example number 6. I'll just pull that down here. So we've got a car moves from traffic lights along a straight road with constant acceleration. It starts from rest at the traffic lights, and 30 seconds later it passes a speed trap where it is registered at travelling at 45 kilometers per hour. Now, before I do anything here, I'm just going to have a look at this 45 kilometers per hour. Now, that's not in standard units, and we always like to keep everything in standard units. So I'm going to first convert 45 kilometers per hour into meters per second. So to do that, if it's 45 kilometers, then I need to multiply it by 1,000. That will tell me how many meters I do every hour. And then to work out the number of meters I do every second, I need to divide it by 60 multiplied by 60. 60 minutes in an hour, 60 seconds in a minute. So divide by 60 multiplied by 60. And I convert that then to 12.5 meters per second. So that must be the speed of the car when it goes through the speed trap. So let's do a quick diagram then. So you've got your car, and it's at these traffic lights, and it tells us that it is from rest. So that means that it's moving with no velocity. It's 0 velocity if it's at rest. Then 30 seconds later, so I know it takes 30 seconds, so the time is 30 seconds, it goes through the speed trap, so the speed camera registers it at going 12.5 meters per second. So in 30 seconds it has accelerated from 0 all the way up to 12.5. And let's again write what we know. So S, U, V, A, T. I don't know the displacement. I don't know how far it travelled. I do know that initially it was moving at 0 meters per second. I know that the final velocity is 12.5 meters per second. And I also know the time. So I don't know the acceleration, but I know the time is 30 seconds. And part A is working out the acceleration. So I'm going to use equation 1. V equals U plus AT. Now I need to rearrange that because I care about the acceleration. That's what I'm working out. So check, you can rearrange that. Acceleration is V minus U divided by T. And then substitute straight in. V is 12.5. Take away U, which is 0, nice and easy there. Divided by the time, which is 30. Type that into your calculator and you should get 5/12 meters per second squared. Obviously, you could put it into a decimal if you want. I'm going to leave mine as a fraction there. Now, part B is working out the distance between the traffic lights and the speed trap. So that's working out the displacement, the S value. And I'm going to use equation 2, obviously. S is equal to U plus V all over 2 multiplied by T. I don't need to rearrange, so I can start substituting straight in. U is 0, V is 12.5, divide that by 2, and multiply by the time, which is 30 seconds. Oh, sorry, can't quite see that. And therefore, if you type that into your calculator, you will get 187.5 meters as our distance. So for part A, we worked out the acceleration, that's here. And for part B, we worked out the distance between the traffic lights and the speed camera. Okay, so once you have finished going through those examples, you should be ready to have a go at exercise 9C. There's loads of questions on exercise 9C for you to have a go at.